Hi, this is Mrs. Cribb, and this is a review video for Semester 1, just trying to hit the highlights of what we've gone over and to make sure you're ready for the second semester. First of all, we're going to go over the periodic table and just remind ourselves of all the things that we have learned about the periodic table. The numbers at the top, right here and all the way across, are called the group numbers. They can be grouped as 1 through 18, or it could be 1A and 2A, and then the transition metals will have different numbers, and this would be 3A, 4A, all the way across. Remember too that these group numbers can tell you how many valence electrons that are present in atoms, and valence electrons are the outermost electrons. So for instance, if I have, let's see, I'll choose sodium right here. Sodium is element number 11. That means that there it is, the atomic number is 11. It has 11 protons and 11 electrons in it. So we'll draw a picture of it. There's sodium with 11 protons in the nucleus, and it's going to have a number of neutrons in the nucleus as well. I don't know what the exact number is. It will have 11 electrons, and there will be 2 electrons in the first energy level, and then up to 8 in the second energy level. 1, 2, 3, 4, 5, 6, 2, 4, 6, 8. Alright, so that's energy level number 2. And then 1 electron in the third energy level. It's bad drawing, but there you go. Now, remember that the innermost part here is the nucleus of the atom. This is the valence electron right there. Valence electron, the outermost electron. Remember that electrons have a negative charge, protons have a positive charge. So 2 electrons in the first energy level, up to 8 electrons in the second energy level. And so that's 10, and then we had 1 more electron in that third energy level, the valence electrons. Remember, these are called the principal energy levels, 1, 2, and 3. And if we look on the periodic table, you can see that the principal energy levels are over here, 1, 2, and 3. And so sodium's principal energy level, the highest one, is a 3. So potassium's highest potential energy level is a 4. Okay, so that was sodium. Let's go ahead and do chlorine over here. Chlorine, element number 17, right below sodium. All right, 17. So this was sodium right here, Na, sodium. And now we're going to do chlorine. Chlorine has 17 protons in the nucleus and some kind of number of neutrons in the nucleus. And then it's going to have 2 electrons in the first energy level. It's going to have 8 electrons, 2, 4, 6, 8 in the second energy level. And then, so that's a total of 10. And then it's going to have 7, 1, 2, 3, 4, 5, 6, 7 in the third energy level. And so it has 1, 2, 3, 4, or 2, 3, 4, 5, 6, 7 valence electrons. And this is for chlorine. Okay, there's chlorine right there in column 17. There's that number 7 and 7 valence electrons. So these group numbers also tell you the number of valence electrons. Okay, so 15 has 5, and this number would also be 5A. Okay, so we have the principal energy levels over here. We have the group numbers that are going across the top, the valence electrons here. And the next thing I wanted to talk about is the octet rule. Remember that the octet rule states that atoms are most happy when they have an octet, which is 8 electrons in their valence shell. Okay? And so they're always working towards getting that 8. And so sometimes that means they're going to be adding electrons, and sometimes they're going to be subtracting electrons. So everything in this column has 1 valence electron. And so it's either we're going to get rid of 1 or gain 7 more. It's easier to get rid of 1. So when you subtract out that -1 electron, you end up with a +1 charge. So this one has a +1 charge. Group 2 metals have a +2 charge because they're going to subtract 2. Then we have those transition metals that have a lot of different oxidation states. Group 3 elements are going to have a +3 generally. And then these guys over here are going to be either positive or negative. Well, group 4 can be a +4 or a -4, and then some more. But group 5A or 15, it's easier to gain 3 than to lose. So they generally have a -3. These has a -2. They're going to gain 2 electrons. So if you add 2 negatives, you get a -2 charge. And this is going to gain 1 electron. And these guys right here have their octet already. So they're inert. They don't react very well. They don't work with other atoms to form bonds. So that's kind of the touching of the oxidation states. We'll go over just a little bit more when we get down to the chart. Other things that you need to remember are metals and nonmetals. And right here would be the stair step between the metals and nonmetals. See? Nonmetals are green. This is the division. And then poor metals over here, or metalloids. So remember on the stair step, right next to it are the ones that are called metalloids. They kind of act like a little bit like a metal and a little bit like a nonmetal. It's really important to remember where the nonmetals and metals are. All these guys over here, nonmetals plus hydrogen, which is its own weird group. And then the metals are all the rest of them, all the rest of these elements. Okay. We also need to remember the names of the metals and nonmetal groups. So if you look at the group 1, give me just a second to erase these guys. Okay. Group 1 right here, not including hydrogen, because remember that's its own thing. So that's these orange. They are the alkali metals. Group 2 are the alkali earth metals. The transition metals are in the middle. And then, of course, you have the boron family, the carbon family, the nitrogen family, the oxygen family. These guys have a special name called the halogens. And right here, halogens. And these are the noble gases. Okay, so those are some of the things we talked about here. Some of the other things we needed to remember is metal, non-metal, ionic. So we need to know that if you have a metal bonded to a non-metal, you form ionic bonds. And ionic bonds is where you have a positive and a negative charge. You have electrons are not shared, they're transferred. Remember? Bond, ionic bond, taken, not shared. And then so that means if you have 2 nonmetals, you have a covalent bond. Co means together, so they're working together to fill their valence shell. So they're sharing. These guys share. These guys take. And then you can also have covalent bonds don't always share equally. So if they have unequal sharing, we have polar bonds. It's unequal sharing. And then if they share equally, we have nonpolar bonds. So that's equal sharing. Okay. So that's still going to become important. So that's the main things down here. Let's talk really quickly about Lewis dot structures. If we have the sodium, it's got that 1 valence electron, and that would be its Lewis dot structure. And we have chlorine, it has 7 valence electrons. So you put them 1, 2, 3, 4, 5, 6, and 7, and that would be its Lewis dot structure. And it shows you the empty spot that's sitting right here, the hole. And so this is a metal, and this is a non-metal. So metal, non-metal, ionic. They're not going to share, it's going to take. So sodium gives its electron to chlorine, so that sodium becomes a +1. And chlorine, its Lewis dot structure now has all 8 valence electrons. It becomes a negative, and we have that intermolecular force. The ionic bond right there where they're attracted to each other because they're opposites. One of the main things with chemistry, opposites are attract. Okay, one more thing that we need to talk about on the periodic table is that the thing about the diatomic elements. So you should have these memorized by now, but hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine. So it makes it 7 over here and this one hydrogen. And when they're diatomic, you write them with a subscript of 2, and that's very important, especially when you're predicting products. So hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine. Very important to keep those in mind. Okay, now this is the oxidation chart you've seen in the past. These list the oxidation numbers that might show up. These are the main ones. Remember that hydrogen is always a +1 unless it's bonded to a metal. So if hydrogen is bonded to a metal, we get a -1 charge. And so most of the time, though, it's bonded to all the nonmetals on this side. All these guys have +1s because they lose 1 electron. These have +2s because they lose 2 electrons. Over here, +3s because they lose 3 electrons. Here's where we start to get a little bit more differentiation on this side, +4 or -4. And then here it's mostly going to be a negative. -3 is the most common one. -2 on this side because we lose 2 electrons, -1. Remember, the charges are how many electrons do you have to get back to make it neutral. So fluorine loses an electron. Sorry, how many electrons do you need to to lose? So fluorine gets a -1 charge because it gains an electron. We got to remember that. That's right. Electrons are negative. So fluorine gains 1 electron. And so if I subtract out 1 electron, I go back to 0. Beryllium loses 2 electrons. So this has a +2 charge. We have to gain 2 electrons to go back to a 0 charge. Because electrons are all negative charges. All right. Remember that the transition metals, all these guys in here, they can have lots of charges. And the main ones that you really need to always think about are iron. We're going to use those. You see that a lot. Copper, nickel. Let's see. I think mercury. These have more than 1 charge. And so since they have more than 1 charge, chromium, you're going to need to use multiple oxidation states when you name them. So, the SPDF blocks. Let's go back up to this one right here. Remember the SPDF blocks? Maybe not. This is where we talk about 1s2, 2s2, 3s2. And so the S is for the spherical shape. And so this is the S block right here. And I'm going to make this even larger because there we go. This is the S block. And the P block is over here. And the P block are these right in this area. All right, and the S block was over here, groups 1 and 2. So S, P, and then the D block was in the middle, and that's all the transition metals. And then the F block is down here at the bottom. Okay? And so that the S orbital shapes are the spherical shapes. The P orbital shapes look like this, like two sides of two dumbbell sides anyway. And you could have one in the x-axis, one in the y-axis, and the z-axis going in and out. Okay? And then the D's there are 5 shapes, and I can't draw them, so D's have 5 shapes, 5 orbitals. The F have 7 orbitals. And in each orbital, you can hold 2 electrons. So the S has only 1 shape, so it has 1 times 2. 2 electrons can be in the S shapes, the S orbitals. The P has 3 shapes, so 3 times 2 is 6 electrons can be in the P orbitals, the P sublevels. The D has 5 shapes, so 5 times 2 is 10 electrons can be there, and 7 for F, so 7 times 2 is 14 electrons can be there. And so let's review how to do the electron configuration and orbital notation of a couple of different ones. All right, we're going to do the electron configuration and orbital notation for calcium. So calcium, we go through the periodic table. We start with energy level 1. So 1s, 1s1, and the 1s2 would be the helium, 1s2. Because remember, for these things, helium can actually sit over here. It's in that weird thing. This is where helium could be. So it's 1s2. And so now we're down to the second energy level. And it goes 2s1, 2s2. And we go straight across to the opposite side. We're still on energy level 2 because that's the principal energy level. But now we're in the P block. So 2p, 1, 2, 3, 4, 5, 6, 2p6. That got us to there, and we go down to the third energy level. So we're back in the S block. So 3s, 1 and 2, 3s2. We go straight across. We're still in the third energy level, 3p, 1, 2, 3, 4, 5, 6. And now we're in the fourth energy level, 4s, 1 and 2. And that gets us calcium right there, 4s2. So that is the electron configuration. The abbreviated electron configuration, remember we go, here's where we are with calcium. It's right, well, let's see. Right here. So we go up one energy level and to the very end. And so that brings us all the way down to argon. So the abbreviated form would be put argon in brackets. And so that calcium contains everything argon has, but then 4s2. So that's the abbreviated form. And then the orbital notation, we're just drawing the electrons. The S shape only has one. The s orbital only has one sublevel, so one electron will spin up and the second electron would spin down. Okay, now we're going to do arsenic. Okay, arsenic is right here. I circled it in red, and we're going to do its electron configuration. So we start off again at energy level 1, 1s, 1 and 2, and then we go to energy level 2, 2s, 1 and 2. We go across, we're still at energy level 2, 2p, and it's 1, 2, 3, 4, 5, and 6. Now we're at energy level 3, 3s, 1 and 2, 3s2. Go across here, we're still at energy level 3, but we're in the p block, so 3p, 6, because we go all the way to the end. And now we're at energy level 4. So 4s, 1 and 2. So we just put 4s2. Now remember, in the middle here, the energy level goes down. So this is energy level 3, and that one would be 4. So now we're at 3 again. 3, D block, lowercase d, and we use all 10 of them. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. 3d10. And remember, it has 5 shapes, so 5 times 2 is 10 electrons. We accounted for all 10 electrons. But on this side, it goes back up a level, so we're at energy level 4 again. 4, and in the middle it's a P. 4p, 1, 2, 3. 4p3. So that is the electron configuration. If we want to do the abbreviated form, we go up a level and go to the end. So it's argon as well. Argon in brackets. It has everything argon has, except it has to add 4s2, so it's adding this stuff right here. 3d10 and 4p3. So that's the abbreviated form. Now we need to do the orbital notation, and I'm going to erase this little pictures of the p orbitals really quickly. All right, so I need we have an s, a d, and a p. Okay. And so for the S, I'm going to put it up here just so 4s2, we do one line because there's only one shape for the S sublevel. the first electron spins up and the second electron spins down. Okay, that's the exclusion principle. One can spin up, one spins down. All right, and then the D, a 3D10, we have 5 shapes, 1, 2, 3, 4, 5. So I have to draw 5 lines for those 5 shapes. And the electrons spin up first, 1, 2, 3, 4, 5, and then they spin down. 6, the 7th one, the 8th one, the 9th one, and the 10th one. And then for the P, for P3, there's only 3 shapes, so 6 electrons. Look in the p orbital, 1, 2, 3, 4, 5, 6 electrons. 3 shapes, 1, 2, 3, and I only have 3 electrons, so I spin up, I spin up, and I spin up. I've got to put 1 electron spinning up each time before I spin down. So hopefully you remember how to do some of that. Okay. Now we're going to go to naming ionic and covalent molecules. Remember, if it's ionic, it's a metal and a nonmetal, and the capital I means you could use Roman numbers, but only if you have more than one charge. So for the metal, for the first thing, so the ones here that I circled have more than one charge, and those are the metals, and so you would use ionic rules with them and Roman numbers. And for covalent, you use prefixes. And you have to remember your prefixes for these. And then we have polyatomic ions where they act as one thing, NO3. And so they just act as one thing, and they have one. I don't know if you heard that. The phone went off. I stopped it. So anyway, these are the NO3s. The polyatomic ions, they act as one thing. They have one charge. And so perbromate, bromate, bromite, hypobromite. This one we have to remember. Per8, 8-ite, hypoite. So per8, 8-ite, hypoite. And these are called oxyanions because they have oxygen and they're negative. And remember, anions are a negative ion, and then you have cations with a big, huge positive sign because cations are positive ions. Here's a cation, this ammonium ion right down here. That's a positive ion, it's a cation. Oxyanions there's a different number of oxygens in them. So the per8s have the most. Notice it has 4, then 8 has 3, ite has 2, and hypoite has 1. Now that's not always going to be true that those numbers happen, but in most of them there are. So look at perchlorate, per8, 4, chlorate, 3, chlorite, 2, hypochlorite, 1. So per8, 8-ite, hypoite. These are just some of the polyatomic ions, and you use them in naming too, as well as naming the acids. So let's practice a couple. Lead 2 phosphate. Lead is Pb. You go up here and you look at lead's oxidation numbers. Here they are. Let's find lead, Pb. There it is. That one I'm pointing to right there. Okay. Now look. It has more than one oxidation state. Metal, nonmetal, ionic. So we have to make sure that it's named like that, and it is. That's why it has this 2. This 2 means use the +2 charge. So lead has a +2 charge, and then phosphate. Find the polyatomic ion for phosphate. Hopefully it's on this. There it is on this chart. PO4 with a -3 charge. So I'll write that. PO4 with a -3. Put the charges on the top, swap and drop. So I move this 3 down to here. And polyatomic ions we have to put in parentheses before we put the the number of them on the side here. A 2. Those are called subscripts. Okay, once I'm done, I don't need that. There's the formula for lead 2 phosphate. The number 2 does not mean how many lead atoms I have. It's the charge of the lead. It was a +2. Now, diphosphorus pentoxide, we're talking about phosphorus and oxygen. If you go back up and look at the polyatomic ion chart, at the oxidation chart, you can see oxygen is over here and phosphorus is right here. They're both nonmetals. So 2 nonmetals is covalent, so we're going to use prefixes. And that's what happened here. Diphosphorus, di means 2, so 2 phosphorus, and pentoxide means 5. You don't have to simplify anything. The name tells you exactly how many atoms are in the molecule. So diphosphorus pentoxide, pentaoxide. Remember, the endings of elements turn into "ide" endings. Okay, now potassium chloride. All right, potassium is a K and chlorine is a Cl. Metal, nonmetal, ionic. So this was ionic and this one was ionic. But potassium up here, here's potassium. It has only 1 charge, so I don't have to use the multiple oxidation state Roman numbers. So just KCl. All right. Carbon monoxide. Well, you know for sure it's covalent because it uses a prefix. So carbon is a C, and monoxide means, mono means 1 oxygen. Carbon monoxide. Remember, you don't say monocarbon monoxide. Mono is the only prefix you don't use with the very first atom. You can use di, tri, tetra, hexa, hepta, penta, whatever, but not mono. Mono you use with the second. You use all the prefixes. Mono, di, tri, tetra. Remember the tetrahedrals. Penta, hexa for 6, hepta for 7, octa, nona, and deca. Those are the main ones we use. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. One of the things I don't have down here is if it has a hydrate. So if I had this same lead 2 phosphate and then it said let's see, 6 H2Os, then this is a hydrate because it has H2O in it. And so the name would then be lead 2 phosphate, and we have to say how many of them. I have 6 of them, and 6 is hexa. So lead 2 phosphate hexa, and if it has water, hydrate. Hexahydrate. So if it had 7, it would be heptahydrate. If it had 8, it would be octahydrate. If it had, and it would still have H2Os there. Now, as far as naming acids, if it's hydro something ic acid, that means it's binary, which means 2 things. So hydrochloric acid would be HCl. Hydro means write down the hydrogen, and then whatever the something is in the middle is the element, and then ic acid. Hydrochloric acid, and it's always aqueous, meaning it's dissolved in water. Now, chlorous acid, we have to remember 8 ic ite us. 8 itis. So chlorous means it came from the ic polyatomic ion. So I go up and find the chloric ion. So here it is. Chlorous means it came from the ite. Chlorous came from the ite. So chlorous, because us comes from the ite. I go back up and find the ite, chlorite ion, and there's the chlorite ion. ClO2 with a -1 charge. So I write ClO2 with a -1 charge. All right, it's an acid, and acids have to have hydrogen in front. This -1 means I need 1 +1 to cancel it out. So 1 hydrogen, and that would be chlorous acid. Let's see, what would CHLOR chloric acid be? Okay, this was hydrochloric, but what is just chloric acid? Well, that's one again where you have to see the ending, the ic. The ic then would come from the 8 ion. So we go back up and we find chlorate. This is chlorate, ClO3 with a -1. Okay, so ClO3 with a -1, and it has to have 1 hydrogen to cancel out this 1 negative. What about one? I'm going to give you one more. Let's see here. I'm going to find one with a, there it is. So SO3. Okay, if we have SO3, it has a -2 charge. Okay, that means I have to have 2 hydrogens. It has to swap and drop again. 2 hydrogens to cancel them out. So this acid, H2SO3, well, what is SO3? Sulfite. So there's SO3, it's sulfite, atic-itis, 8 becomes ic, and ite becomes us. This is an ite, so instead of sulfite, if I had H2SO3, it would be sulfurous. Instead, because it's got it's sulfuric acid and sulfurous. This is sulfurous. It has sulfur. So sulfurous acid. So ite became us. The ite ending became the us acid. Sulfurous acid. All right, balancing equations and predicting products is going to be the last thing that we cover on this. Okay, this first one, we have sodium chloride and fluorine. And for what can happen? Well, we have this single thing right here, fluorine, all by itself, and it's got a subscript of 2 because it's diatomic. Fluorine is going to take the place of chlorine. If you look on the periodic table, let me scroll back up here real a minute. Here's fluorine, chlorine, bromine, and iodine. Okay, and fluorine is the most reactive at the very top, so it can replace everything below it. Chlorine could only replace bromine and iodine. Chlorine could not replace fluorine because of the activity series. Fluorine is the most reactive. Okay, so we go back down to the bottom. Fluorine can replace chlorine, so this is a single replacement reaction. And so fluorine replaces chlorine, so we write sodium with the fluorine. Okay, sodium has a +1 charge and fluorine has a -1, so swapping and dropping, this is already the formula. And then we have to put chlorine, and chlorine is one of the diatomics: hydrogen, nitrogen, oxygen, fluorine, chlorine. So we have to put a subscript of 2. So we predicted the product, and now we balance it by writing the elements and counting them on both sides. We have 1 fluorine to 1 on the product side. Remember, this is the reactant side. This whole side is reactant, and this whole side is the product. We have 1 chlorine to 2, and we have 2 fluorines to 1. All right, so I need to have 2 fluorines on this side, so I'm going to put a coefficient in front of a 2. You can only write coefficients in. You can't put in subscripts. So now that changes my sodium count to 2 and my fluorine count to 2. So I need 2 sodiums on the other side, so I put a 2. That changes this sodium count to 2, and now I also have 2 chlorines, and it's a balanced equation. Okay, let's do a different one. All right, here we have aluminum. Aluminum has a +3 charge. I can go back up and look on the on the oxidation chart and find aluminum. Here it is, +3 charge. And bromine has a -1 charge. Potassium has a +1 charge, and this is sulfate, SO4. Go find sulfate right here with a -2 charge. So we have a positive and a negative and a positive and a negative. That's like 2 dancing couples. They swap partners, so this is going to be a double replacement reaction. So this positive will go with this negative. So we have aluminum and SO4. Now we put the charges on the top. Aluminum is a +3 and sulfate is a -2, and then we swap and drop to determine the formula. We don't just say there's 1 and there's 1. We charges on the top, swap and drop. Bring the 2 here, put the polyatomic ion in parentheses, and bring the 3 down. And now we have that. That's aluminum sulfate. And this positive goes with this negative. And remember, we always put the positive, the cation first. Potassium has a +1 charge. Bromine has a -1 charge. And that's all it is. Okay? So potassium bromide. This is metal, nonmetal, ionic. But potassium has 1 charge. This is metal, nonmetals too. It's also ionic, but since aluminum only has the +3 charge, it's just aluminum sulfate. So now we're going to balance it. We list aluminum, bromine, potassium, and I can list sulfates because they're both on both sides. So SO4s. We have 1 aluminum on the reactant side right here and 2 on the product side right here. We have 3 bromines on the reactant side, 1 on the product side. We have 2 potassiums on the reactant side and 1 on the product side. We have 1 sulfate on the reactant side and 3 on the product side. And so we got to do a little bit of moving around. We need 2 aluminum, so I'm going to put a 2 in the front. Now I have 2 aluminum, and 2 times 3 is 6 bromine. Okay, I need 6 bromine, so I'll put a 6 here. That's going to give me those 6 potassium, because I have to change everything in there, and 6 bromine. Okay, I need 3 sulfates or 6 potassiums. So if I put a 3 in the front, that'll give me 3 times 2 is 6 potassiums, and 3 times 1 is 6 sulfates, and that is the balanced equation. Okay, we're going to do one more. All right, what we have here is a fuel. This is actually octane, and I don't expect you to know the name of that one. And then it's reacting with oxygen. And remember the little symbols? I could put a little delta on top of this arrow, and that would mean add heat to make this reaction happen. This is a combustion reaction. You would just have to recognize the fuel. Combustion reactions always form carbon dioxide and water. And so now we need to balance it. And this one is actually pretty easy to balance. I wanted the carbons divisible by 4. Now this one might end up giving us a little bit more trouble, but we're gonna, the carbons are already divisible by 4, so that usually that helps us. So let's give it a shot. We have 8 carbons on this side and 1 on the other side. We have 18 hydrogens and then 2 right here and 2 oxygens and 3. We have 2 of them here and 1 of them here. All right, I need 8 carbons, so I'm going to start off by putting an 8 in front. It's going to change my carbon count. Now how many oxygens do I have? Now I have 8 times 2 is 16 oxygens plus 1 more, that's 17 oxygens. And that's not going to be awesome. I need 18 hydrogens and on the other side, so I'm going to put a 9. Okay, because they come in groups of 2. So that gives me 18 hydrogens. Okay, now but how many oxygens do I have now? Well, I did have 17, but now I have 8 times 2 is 16 oxygens plus 9 more, and that's 25 oxygens. Okay, now 25 oxygens. You know, before I said make the carbons divisible by 4. Well, 8 is divisible by 4, but this is one of those cases where that rule isn't going to work, because if you did made the hydrogens divisible by 4, if I put a 2 in front, then it would work better for the hydrogens. And so sometimes you have to just check and see, and this is one of those cases where it doesn't work perfectly. So I'm going to actually use the fraction rule on this one, which we haven't done a whole lot. So I need 25 oxygens, so I put 25 here, and they come in groups of 2, so 25 halves. The reason I'm doing that is 25 over 2 times they come in group of 2. If I multiplied that together, I would get 25 instead of 50. See, if I just put a 25 in front times 2, that's 50. So now that I have the 2 on the bottom, I'm going to multiply the entire equation by 2. And I rewrite that then as 2C8H18 plus 25 O2s yields 16 CO2s and 18 H2Os. Now, let's just check the count. Let's recount. So 2 times 8 is, now we have 16 carbon here and 16 on the other side. 2 times 18 is 36 hydrogen on this side, and then 18 times 2 is 36 hydrogen on the other side. Now oxygen, we have 25 times 2 is 50 oxygen. Here we have 16 times 2, which is 32 oxygens, plus 18 more oxygens from right here. So 32 plus 18, that's 42 plus 8 is 50 oxygens, and it balances. So I did this whole fraction thing, which you may not have seen a lot of, but I could have gotten around this one if I would have said, okay, instead of making the carbons divisible by 2, I'm going to make the hydrogens divisible by 2, because 2 times 18, divisible by 4. 2 times 18 is 36, and 36 is divisible by 4. 36 divided by 4 is 9. Even though the carbons were already divisible by 4. So you see, every time it doesn't work to use the carbons. Sometimes you have to use the hydrogens. Okay, even though we're not going to balance anymore, I'm going to show you the other types of reactions just so we can review them. Okay, here's 2 more types of reactions. Now we're just going to figure out what kind they are. We have 2 separate things, and on the product side I only create 1 type of molecule or atom. So this is a synthesis or combination reaction. On this side I have 1 molecule, and it falls apart into 2 types on this side, so that is decomposition, the opposite of synthesis. So that's the 5 types of reactions we've covered. Single replacement at the top right here, double replacement where we do a partner switch. Now remember, with the single replacement you always end up with a different single on the product side. Combustion, where you always end up with carbon dioxide and water on the other side. Synthesis and decomposition. Okay, and then the last thing we've covered this semester talked about the liquids and cohesion and adhesion. But these are the main things you're going to need to remember to go into Chapter 9. So I hope this helped, and I guess we'll see how it goes next semester. Talk to you later.